Good morning, everyone, and welcome back. Please ask everyone to respect the presenters here and give the focus on them because they've spent a lot of time on their presentation. So next, I am going to we're really working into the part of the program where we're going to focus on what we've done here in Lake George and our science to solutions approach. And with that, we'll start with the science. And it wouldn't be a SALT Summit if we didn't have some science, and we're really honored to have what I'm going to call the three doctors here to come up and talk. I'll just call it the magic model, and you will let them talk to you about what it is. But my good colleague, Dr. Jim Sutherland, who has been working with the Lake George Association as a science advisor for years, retired New York State DEC. And with all the love and respect in my heart, I call him the father of Lake George hydrology. We have Dr. Steve Norton. Steve is an Ivy League educated and taught at the University of Maine for 40 years until his retirement in 2008. He continues to improve the lives of young adults through a scholarship endowment he established with his siblings in memory of his mother. Through their 4 endowed scholarship funds, the family has created at the University of Maine a foundation. Their legacy of kindness has changed the lives of many University of Maine students. And Dr. Jack Cosby, who is the person that traveled the longest, I think, to get to our summit. He came from England and to present. Jack's interest is in chemical and physical processes in the environment, and we're initially focused on groundwater in catchments and hillside hydrology. So without further ado, I will invite the three doctors, or one by one, to come on up. So please welcome Dr. Jim Sutherland.
Thank you, Chris. I've worked with Chris now for, 12 years, 13 years. So instead of the father, I'm now the grandfather. And I'm going to try to keep going as long as I can. Drawing on a couple of the previous presentations this morning, Allison and Jennifer, there were some key words and phrases that they mentioned. Monitoring was one of them, and when you put the road salt down, it disappears was the other. Because that really ties into what our whole presentation is about. We're covering a period of 55 years of monitoring that has really led us to answer some questions about what's happened. And part of the objective here was to determine what happens when road salt is put down. Because she's right, it does disappear. But it doesn't stop working. It gets into the soil and it causes certain interactions. And that's what you're going to hear about today. And I know there are a lot of people in here that are not necessarily, have a big background in science, but it's the monitoring that really tells us in the long term whether or not what we're doing is working. Because what we're doing here is keeping track of water quality, and that's what tells you whether or not this salt reduction program has been effective. So basically, we're going to talk about a manuscript that we recently submitted for review, the chemical evolution of tributaries to Lake George, 1970 to 2024, recovery from acidic atmospheric deposition, and the impact of road salt. And this presentation involves the three of us, myself, Steve Norton, Jack Cosby, a brief summary of their credentials. But I would also be remiss if I didn't mention Chris, who I've worked with for all these years and who I respect for his effort and the fact that he was key starting this whole program 10 years ago. So thank you, Chris. I also, because sometimes this gets pushed aside, but I just want to have a slide of acknowledgments. Because our story starts back in 1970. Someone named Wolfgang Fuß, who was then the head of the New York State Department of Health, laboratory, the environmental science laboratory down at the South Mall, and then the list goes on up through the present time. And there is one omission on this list that I'm very sorry about, but it's the Lake Champlain Sea Grant Program. So some of you are probably wondering, well, why are we talking about acid deposition? We're here to talk about road salt. And drawing on a quote from my colleague, who I just met 3 days ago, Jack Cosby, we have to understand all of the stresses that occur in a body of water before we can manage the current stress that we're trying to focus on. Our current stress here today is road salt. But acidic deposition was a previous stress on Lake George. We didn't see it impact the lake the way we've seen it impact the lakes and ponds in the Adirondacks, where I worked for most of my career. But it did have an impact because the acidic deposition was falling on the watershed, the drainage basin, and it was having an impact that was silent. It's beneath the surface. So the whole concept, watershed acidification, deacidification, and road salt loading to the lake itself overlapped in time. And these two phenomenon, these two stresses, disrupt similar equilibria in terms of their impact on the adsorption and desorption of ions in soil. Acidification is driven by the H ion. Salinization is driven by the sodium ion. H ion from acidification and the sodium ion from salinization interact with cations in the soil, specifically calcium, magnesium, and potassium, in a similar manner. So this is even more credence as to why we have to understand one process in order to interpret what's going on now. The journal we have submitted was submitted to, the acronym is STOUGHTON, Science of the Total Environment. The four co-authors, we evaluated 18 Lake George tributary watersheds that comprise approximately 39% of the terrestrial drainage basin around the lake. And over this period of 55 years, we had 4,000 plus data points that we looked at, beginning with the samples of Wolfgang Fuß when he did work on tributaries in Lake George during 1970, 1971. Our sampling strategy, and luckily for us, the sampling strategy of Wolfgang Fuß back in 1970, was to look at upper areas in watersheds that were not affected by any development, and lower areas, primarily very close to where the tributary would enter the lake, where there was a maximum of development and its impact. And having these two segments, unimpacted and impacted, was really what gave us the ability to evaluate these data so that we could say what was happening, the trends that were occurring, the magnitude of the changes, and the overall process. So acid deposition was really the first stressor, probably began sometime post-World War II. As I mentioned previously, the preliminary work in Lake George is the first indication of any tributary work in Lake George at all that I'm aware of. It was Wolfgang Fuß, 1970, 1971. The samples he collected in 1970 were just about 10 years prior to the maximum impact of acidification that occurred in the Lake George Basin. This is a map that shows the dotted line is the outline of the Lake George terrestrial drainage basin. The solid lines within the dotted line are the different tributary watersheds that we looked at around the lake. And as I mentioned earlier, they comprise about 39% of the drainage basin. I apologize for this busy slide. I hate it when people do this, but I did it myself. This is a table that's in the manuscript, but just to give you the basics, the far left-hand corner or column is the name of the tributary watershed. The ID number is the T number that DEC assigns to the tributaries around Lake George. The rows across the top show the different time periods during which data were collected. And then the meat of the table shows how many samples were collected during each of those time periods. And the numbers behind the number of samples are whether or not the watershed was sampled above, below, or both above and below. And the far right-hand column is the total number of samples we collected over that 55-year period. Okay, now I'm going to talk a little bit about climate change in the Lake George drainage basin. And in order to assess climate change, we went to the nearest NOAA, National Oceanic and Atmospheric Administration climatological station, which is located at the Glens Falls Airport, just south of here. And we looked at 55 years of temperature and precipitation data over that period. The graph on the left, what we did first of all was we separated the year into two periods. If you look at winter, at least in this area, winter is from when the first road salt is applied, generally in November, through April. And then we took the other period, summer, which would be May through October. Overall, there's been a 2.5 degree temperature change within the Lake George Basin during the past 55 years. The summer temperature is increased by 1.5 degrees, and the winter temperature is increased by almost 3.5 degrees. This is the precipitation data, a lot more scattered, but it does give us a trend line, and the data are real. The annual mean precipitation in this area has increased by 0.6 of an inch. The summer mean precipitation has increased by 2 inches, and the winter mean precipitation has decreased by about 1.5 inches. And these data are real, and they may not directly apply to Lake George per se, because the basin is separated from the airport, but it's the closest record of data that we had to analyze for that length of time. So now I'm going to introduce my colleague, Steve Norton.
Oops. I was apparently introduced by a previous speaker who said white hair. Well, I personify that. I've known Jim for about 12 years, I think, and I think that he deserves a round of applause because it was he that personally or directed the collection of these 4,335 samples, and much of it by himself, which is now against OSHA rules and so on, but I applaud Jim for his love of... I'm the data guy, and I will be followed by Jack Cosby, who is the model guy. Last winter, I went out on my brick patio and I collected a few grains of road salt. And there they are. And there are some curious right angles in the salt. And that's going to be very important in the sense of the solubility of that particular mineral, which is, we call it, as a geologist, which I am, halite, sodium chloride. But first, I want to talk about the demise of acid rain, at least the sulfate part. So we had samples going all the way back to 1970, and you can see the time is marching forward on the horizontal scale, 1970 to 2024. And fortunately, we had Foos, and he was a very good chemist and a lot of data. And going back in 1970, there are samples from Upper, unimpacted, and lower sites in 3 and 1 cases, respectively. This is a very complicated vertical scale. It's the mean of means, mean of annual means. So in the case of the uppermost brown dot there, there was only one sample that was upper. But there were 3 samples of different tributaries shown in green, and they typically had a little more sulfate. I put a linear regression through those, which you saw earlier in one of the speakers' talks. And so I thank you for setting the table for me. If you followed that, you should ultimately be able to follow this. But the green dashed line is drawn through, it's a linear line gone through all of the lower tributary samples that we have. And a straight line fits it fairly well. The brown line is all of the upper tributaries. And we have fewer of those, but still, we get a very high level of confidence that it is a linear relationship. So sulfate has gone from, depending on whether you're looking at upper or lower, from about 15.5 all the way down to 3 for the case of the lower, the upper tributaries, and the green is about 4.5 for the lower tributaries. That is what is coming out of the soil, because as you will see in the next slide, the amount that's coming from the atmosphere now is trivial. Trivial. Acid rain has gone away. The pH has gone from the mid-4s around here to about 5.5. And if you know about pH, you don't want your soils to be too acidic in your gardens, but the forests don't like that either. There just happened to be 3 precipitation stations that are located in close proximity, really, to Lake George. One of them is shown in red, which is Bennington. One is green, Huntington Forest, and Passaico Lake, which is sort of west of here. They're all within about 40 to 50 miles of Lake George. And so I've plotted them on the lower part down here, and for the people on the left-hand side, this is Passaico Lake in yellow, and Bennington in red, and Huntington in green. And I put linear regressions through those. And I left the upper tributary graphic, which is brown or orange, on the same graphic. So you can see that there is more sulfate coming out of the soils, as determined by the vertical scale there, the concentration of sulfate. There's more sulfate coming out of the soils than we have coming from the atmosphere. And this has been true ever since about 1980, when emissions reached their peak for sulfate, emissions from burning of coal and gas, and actually not gas, but other fossil fuels, such as petroleum, and then the smelting, of course, which has occurred in our country. So, more sulfate coming from the soil than coming from the atmosphere. The outlet of Lake George is shown in purple. And so the upper tributaries lag behind, Lake George itself, the outlet up in Ticonderoga, that lags by about 10 years, 8 to 10 years. That just happens to be very close to the half-life of water in Lake George. So that makes sense. But what doesn't make sense until you understand it is, why do we have this business of much more sulfate dissolved in the waters of Lake George than is coming from the atmosphere? I put some linear equations on this map of quality, water quality, and I just arbitrarily said, I wonder what the sulfate looks like if we just connect the dots. And it doesn't look quite the same as a linear regression, but still, you can see that you start up high and you end up very low in the upper tributaries. And the outlet is still the same, and the atmospheric deposition is shown by the red, green, and yellow. Well, here's the reason why we have little cubes of salt, because the structure of sodium chloride is such that we have big chlorides, and I guess I got to break one of these out. Big chlorides, which are negatively charged, and little tiny sodiums, which are positively charged. Something that's in solution, if it has a negative or positive charge, it's called an ion. So we've got positively charged ions and negatively charged ions, and we have to figure out what happens to that road salt when we put it into water, or when you put it together with snow or ice. On the upper left-hand part of the screen, we have the word solubility. That's how much can dissolve. Well, the solubility of sodium chloride is about the highest of all the naturally occurring substances. And it just dissolves, as shown. Sodium chloride becomes sodium ion and chloride ion when it's in solution. There's also a term, speciation, and water can speciate into, as shown by that equation, hydrogen ion and hydroxyl ion. And if there's a dominance of hydrogen over hydroxyl, the product of those two, the one times the other, must equal 10 to the minus 14th. So if you've got a predominance of hydrogen ion in that water, then we say it's acidic. And if there's a dominance of hydroxyl, then we say it's basic. That's all for that. But here is a particle magnified enormously of soil. And within the soil, you can see a lot of little negative signs or minus signs. They're scattered all over the surface, and that's just the way of nature telling us that minerals, such as sodium chloride, all the metals are small, and all the other things, oxygen, for example, is negative and on the surface of that soil particle. And thus, we have an inner sphere of what is called exchangeable hydrogen and aluminum, forming a cover on a soil particle. That blanket of positive charge now attracted to the negative soil particle attracts sulfate and phosphate. That is the sulfate that's coming off the soil. So eventually, that soil will come back into equilibrium with the atmosphere, but the atmospheric deposition, which is collected by those 3 sites called the National Atmospheric Deposition Program, that will finally, well, that atmospheric deposition gets magnified because of what's called dry deposition, foliage, gaps in foliage, the type of foliage, and so on. So that what comes out of the soil will always exceed what comes in from the atmosphere, but it still may decline a little bit more. So if we flood that soil particle with sodium, the sodium will kick off aluminum, hydrogen, and so on, and in so doing, that sulfate will come off. So it's a continuous process, and I liken it to a bank account. How many people here have bank accounts? Yeah, we all do. And we know that if we always put in the same amount every month, that eventually we get into some sort of an equilibrium, because you don't want to do deficit spending. You don't want to just accumulate a lot of money in the bank account. And so you come to a situation which we call equilibrium. That gets disturbed by the sodium. So the bank account starts to be lost. And the first thing that is lost, not shown in this slide because the soil pH is higher, is calcium. And the second thing that comes off with salt is sodium. And the third thing that comes off in excess is potassium. So you can break the bank if you overspend. And that's what we have done. And we've heard about various examples in this state and out of state. So here are some data from 6 lower sites plus the outlet. And I've changed colors on you to confuse you. But let's just look at one, the red one. Or let's look at the black one, because that's our poster child. In our publication, that's our poster child. We picked that one simply because there's a lot of data, and we have data going back to 1970 and so on, and abundant data per year. So the black line that you see going through, and note again that the calendar is down below, and the amount of calcium in solution, units are not important, starts off at about 8. By 1980, it's up to 17. And by 2007, it's up to, 23. And then it crashes, and we are not sure why this crash occurred. And it crashes all the way down to 15, it wobbles around, gets a little bit lower, and then increases up to about 17 or 16, and then crashes again. Now, from 2016 onward is roughly the lifespan of your program for reducing salt. And I'd like to give you full credit for that, but I can't, and I'll show you why. I can give you a lot of credit. So it goes down and down and down so that in 1924 or 23, it is actually less than what we had in 1970. So they all show the same behavior. Some have more calcium, some have less calcium, some started out with less calcium, and so on. But every one of them, I mean, the light blue one, for example, it's not much data, but it went through the same kind of excursion in time that is shown by all the others. Unfortunately, not every year was collected, and so there are no data for Indian past 2016 that involve calcium and time. The next three slides are identical except for the vertical scale. First, we have a difference in the symbols. In the lower left-hand corner, there's a rectangle. That rectangle includes all of the data collected at upper sites. So one could say that's almost background now, if we are recovered from acid rain. The next sample, and now they're keyed, I should say, to the inner box which shows time. So what I'm going to do is walk you around on this particular graphic and show you what happened to the amount of calcium, and each symbol represents a step in time. The triangles will give you a nice, interesting trip. So in 1970, in the little box there, the blue arrow goes from background, which we'll call it, for lack of a better term, but they're all upper sites, up to, goes from an average of about 100, and it goes up to 230. And then in 1980, it goes up to a little over 400. And then it dips a little bit, and then it climbs again back to 400, and then it does a loop. What we call this is a positive hysteresis, or a clockwise hysteresis, and by 2019, it was the pink with the blue perimeter, and then it jogged a little bit back up to the green symbol, and then it crashed, and it sort of circulated around that red dot with the black rim. I guess it's a blue rim here. So that is getting very close to background. And another point that I want to share with you is that the second triangle, the blue one, which is 1980, the sodium in that was about 700, a little over 700. And even though the sodium went up, what happened to the calcium? It fluttered a little bit, but it didn't respond very much to the massive increase in sodium. The bank was broken. And then when we went through, or you went through, a chloride decline or a sodium decline, the return trip was, I mean, I can only point over here. When we get down to 700, there's been an 82% reduction from the bank for the same 700 micromoles of sodium per liter. Again, units don't matter, but you can see it graphically that there is a great long journey that ends up with a lot of sodium and chloride in the water. However, it's not the same soil. It has lost a lot of calcium, magnesium. 93% of the magnesium is gone from the bank account, and potassium. Now the lines disappeared, but you can see the pattern. So what we have in English Brook is typical of many other streams that have been salted, and we have essentially stripped a lot of calcium, a lot of magnesium, and a lot of potassium from the soil. Now, calcium is kind of important. Zebra mussels, you've all heard of zebra mussels, or you should have. Zebra mussels require about 12 or 13 or 11, depending on the life stage, I guess, milligrams per liter. All of Lake George got to 14.14 actually, I think it is, 14.14 milligrams per liter, the whole lake. And zebra mussels got established because somebody came in with a boat that wasn't properly washed. However, the calcium now is being diluted because calcium, I can back up 2, if you can do that. Yes. The calcium is now, that is being discharged from all of these salted streams, is diluting Lake George. Diluting Lake George. So calcium and magnesium and potassium in Lake George are being diluted. It's kind of an amazing thing. The bank is broken. There's very little exchangeable, desorbable calcium, magnesium, and potassium left in the soil. And when we get down to weathering rates, which Jack can talk about a little bit, how much is normally released by the watershed for calcium, magnesium, and potassium, we will find that it's going to take a long time, perhaps decades, for Lake George to recover. But it's headed in the right direction now. The calcium is down to about 11 milligrams per liter, which means that only certain streams that have high calcium will be able to supply enough calcium for zebra mussels and Asian clams and a few other species. So I will now introduce Jack, and he will tell you about the recovery from acid rain, perhaps in just one sentence, but also the role of sodium chloride in working forward. There you go.
Thank you.
Hello, I'm not good. Yeah, so anyway, next steps. We've got this fantastic data set, 50 years worth of data. There's a lot of stresses on Lake George during that 50 years, and another one developing besides road salt, which is climate change. What are we going to do with these data right now? And basically, this is about our plans on doing some modeling work. Because of the way the sampling is set up, you know, we can sort of look at the effects of the road salt applications in the lower reaches of the basin. Can I go forward? There we go. And the model that we're going to use to do this, because it involves soils, is a model that was used all throughout the acid rain program in the US and abroad, something called MAGIC. And just a real quick little anecdote. We named it MAGIC. It is an acronym. It means Model of Acidification of Groundwater and Catchments. But we wanted to hear the administrators at EPA saying, if we're going to solve this problem, we'll have to use MAGIC. And we did hear them say that, so, at any rate. So MAGIC, it is about long-term simulation. It involves soils. It can look at both inputs of neutral salts like road salt, as well as looking at acid inputs. Real quickly, it looks at all the aspects of what go on in an upland ecosystem, atmospheric deposition, road salt, how climate change affects those inputs in terms of storm frequency, in terms of water quality. It involves land use, which is something we haven't really talked about. What affects the soils also is how that soil has been managed or farmed or forested or afforested through time. All of that goes into the model, and we have these really good data sets to try to calibrate that model to see what it means for the long-term future of Lake George as all of these stresses either recover from each other or start to pile on top. To start with, we've picked 4 test catchments to apply the model. Basically, we're looking at the 2 test tributaries of the DOT Route 9 North pilot program, so we can sort of look at reductions of road salt and see if we can begin to see recovery from road salt like we can see recovery from acid rain. We also are looking at a long-term tributary, Finkelbrook, which is one of the, there's so much complicated land use, development. We're going to use that as one of our other sort of experimental sites to see what other aspects of chemistry we might be missing. And here's just a couple of real quick slides just before we finish up. Basically, the sulfate you saw, Steve showed you that, upper left corner. Those plots on the top tube are all 18 tributaries. On the bottom is just the averages from the 5 we're modeling. So we've chosen 5 modeling sites that look just like all the rest of the tributaries. Sulfate you've seen, it's coming down. Chloride, though, is very interesting. Upper right corner, that's all 18 tributaries. You can't put a single linear regression line through that. You have to break it in the middle, and that break occurs right about 2015, which was the beginning of Salt Summit. And it's been a steady decline in the tributaries all across Lake George since that time. The the black line on that plot, that's Lake George outlet. So the tributaries are coming down. We see effects of what's going on. It hasn't shown up in the lake yet because the lake has a long turnover time itself, but we're getting there, as people have said. One quick last slide, and here's where the complex situation comes in. If we look at sodium, we see sodium follows the same trajectory as chloride. So it is a road salt effect that's happening in there. As Steve pointed out, calcium has responded in a similar manner. And this is potentially one of the unexpected consequences. Road salt itself affects sodium, affects chloride, but it also affects other things that have ecological importance in the lake, like calcium. And the unexpected benefit could be either good or bad. In the sense if calcium is coming down, that makes it harder for zebra mussels to survive. That's an unexpected benefit of road salt reduction, in addition to human health benefits and all the others that we've talked about. So this is why we want a model to feed into the Great Lake George models that are already in place, all the hydrodynamics and circulation, what we know about what's going on. We provide this chemical input from the soils and trying to put this all together. So Jim, I'm going to call you up real quick. We're going to use these models to do some scenarios. We're going to look at potentially the interaction between deposition and road salts. We can also use these models to look at how and how much road salt's applied. And it keeps coming up in the background, but what's climate change going to mean for all these plans in the future? More intense storms, less frequent storms, that affects salting, that affects recovery rates, that affects how the systems can be managed. So with that, Jim, you please come make our conclusions, if you will.
Thanks, Jack. So just to reiterate some of the things that have already been mentioned in this talk, the local efforts have worked in terms of the road salt reduction program. So congratulations to everybody that's been involved in that, that's in this room. Thank you. Along with that, we also are seeing climate change. Sometimes that's not so good. The weather has become a lot less unpredictable. But the good thing is, in terms of the warming and the precipitation reduction, we're having to apply less road salt as a result of that. Continuing these best management practices will mean likely that we'll continue to see reductions in the cation concentrations that are in Lake George. They're currently being reduced and diluted. That should continue. As Jack mentioned, Steve mentioned, we're not able to predict when full recovery could occur, but that's why we're using the MAGIC model and the data that we've got to try and determine that over the long term. Lowered calcium, again, as Steve mentioned, zebra mussels, some other invasives like Asian clams. The populations have probably become reduced lake-wide because of the reductions in calcium in the lake. They still have refugia at the outlets of certain tributaries where the calcium concentrations are high enough, but certainly in terms of a lake-wide basis, they've become reduced to a great extent. And also, we just want to conclude by saying that, this involved a lot of different studies, many of which I was involved in, that involved stormwater runoff around certain developed areas in Lake George. We're just glad that we were able to use all of these data in one spot to make this evaluation and show in this room today how successful the road salt reduction program has been. Thank you.